everyone, welcome back to the practical session on NeuroSynth-Compose. My name is Yifan Yu. Today I'll be talking about meta-analysis, specification, and execution. If you want to know more details, you can also check out the companion book with the link below. I guess you have already heard about the flowchart illustrating the important 8 steps of a meta-analysis. If not, you can check about more details in this paper, 10 Simple Rules for Neuroimaging Meta-Analysis. So among the 8 important steps, after annotations and data extractions, we are now at step 5, where we need to make a decision of the specific meta-analysis that we are going to conduct, as well as the potential sub-analysis. For example, we need to decide the meta-analysis method, correction method that we are going to use, as well as the corresponding parameters. As for the step 6, the conversion of coordinates into the same reference space has been done by NeuroSynth-Compose behind the scene, so you don't need to worry too much about that. Today's talk will be mainly focused on steps 7 and 8. In step 7, the calculation of meta-analysis is automatic and has been designed into a pipeline as long as you have chosen the meta-analysis method, correction method, and the corresponding parameters. And it will generate a transparent report where all the necessary data will be provided for the replication of meta-analysis. It will also generate flowchart, including number of experiments and other important summaries. It can also answer some of your other research questions. If we have a look at the project stage, after finding the dataset, curation, extraction, annotations, we finally reach the specification stage, where we select and parameterize the meta-analysis algorithms, and then the execution stage, where we run and upload the result of the meta-analysis. In these practical sections, we will be using the nicotine administration dataset as a meta-analytic dataset, which includes 39 studies in total. If you want to know more about this dataset, you can check out the paper above. If you haven't finished the previous extraction and annotation step, you can use our pre-run meta-analysis by using the 12-character ID highlighted here. Now I will start with a very short recap. Using the Prisma workflow, which was mentioned in the previous lectures, we know it includes 4 steps, which is identification, screening, eligibility, and inclusion. According to this criteria, we import and include all the studies from nicotine administration dataset. After adding annotations, which is either activation or deactivation for studies involved in this meta-analysis, if the studies has already existed in the meta-analytic database, we can import the coordinate table directly by using the DOI OHBM ID of these studies as shown here. Otherwise, we should extract coordinates from each studies and manually add it into a table. Now, if you have a look at the NeuroSynth-Compose workflow interface, there are 3 steps when editing the projects, and we have already finished the first 2 steps, and now we will create a meta-analysis specification by click the button and proceed to meta-analysis page. Then we will be directed to a web page where there is a button for creating meta-analysis specification, and after successfully specify and execute meta-analysis, there will be a box for viewing the meta-analysis result below. The first step to create meta-analysis specification is to select studies for the meta-analysis according to the previously added annotations. For example, we can only choose the nicotine administration studies with the activation annotations, or only the nicotine administration studies with the deactivation annotations, or all the nicotine administration together by selecting the annotation inclusion column here. The second step is to choose the specification of meta-analysis algorithm and characters. All the coordinate-based meta-analysis algorithms follow the similar procedures. It starts from combining peak coordinates across studies, and then applying kernel convolution at each peak coordinates, which would give rise to the peak density map or ALE map. Then we apply significance threshold to give us significant result. Here, for the illustration purpose, we will use the most common meta-analysis algorithm, ALE, but NeuroSynth-Compose also supports other options of meta-analysis algorithms. For example, ALE subtraction, KDA, MKDA, and scale. Here we can also specify the algorithm arguments below. For example, we will use approximate as the num method because it's faster, although it's slightly less accurate, and we will use 8 as the kernel FWHM, or otherwise we can provide kernel sample size, but these two arguments are mutually exclusive, and there is a practical rules for computing the FWHM by providing the sample size. Before talking about the specification of correction method, I will briefly introduce the multiple comparison problems. Just imagine if you have 100,000 voxels and alpha equals 0.05, it will give rise to 5,000 false positive voxels. 5,000 is a large number if we don't adjust for multiple comparison problems. Therefore, we need to control either for family-wise error rate, which represent the existence of one or more false positives, or we need to control for false discovery rate, which is the expectation of the number of false positive voxels divided by number of all voxels declared positive. If we have a look at the figure on the right, there is noise in the background with the signal. If we don't control for multiple comparison problems, we will get these dots in the background, which is the false positives. Well, if we control the family-wise error rate or false discovery rate at 10%, we get higher signal-to-noise ratio. The step 3 is to choose correction method for multiple comparisons. The NeuroSynth platform supports both FDR character and FWE characters. Here, following the method in the paper, we use FDR character with independent method, and we choose alpha to be 0.05. Before launching Google Colab and conducting meta-analysis, we can review and edit the parameters in the selected meta-analysis specification. So here we can find the parameters for ALE algorithm and FDR character as we have set up before. The NeuroSynth-Compose platform provides two options to run meta-analysis. You can either run it online while Google Colab or run it locally while Docker, but we strongly recommend you to run it online while Google Colab because it's easy and it doesn't require any environment setup. And please make sure that you copy-paste the meta-analysis ID below, which will be useful later. The Google Colab will be generated according to your selected meta-analysis method, correction method, and the corresponding parameters. After being directed to the Google Colab, please follow the instructions to install NiMARE, paste the NeuroSynth-Compose meta-analysis ID, and run the selected meta-analysis. After running the selected meta-analysis, NiMARE will generate a report which we can either download or view it in Google Colab. It includes an overview of the coordinates input, for example, number of studies, number of experiments, and number of foci, as well as a visualization of brain mass which is used in the meta-analysis. It also includes a visualization of peak coordinates from all studies. They are presented in different colors, so you might get an intuitive idea about the distribution of peak coordinates from different studies. It includes a parameter summary of estimator and corrector for the selected meta-analysis. It reflects the parameter settings that we have chosen earlier. It also includes both interactive and static visualization of the FDR-corrected meta-analytic map. The highlighted areas represent activation regions with activation intensity higher than the average. The table on the right indicates the 24 clusters detected in FDR-corrected day map with the voxel-wise threshold 1.65 and cluster size threshold 10. X, Y, they are the coordinates of center of mass of each cluster. Here, positive tails means the convergence relative to the non-distribution, so the label map below represents the location of 24 clusters, which are presented in different colors. We also run focus count analysis to categorize relative contribution of each experiment to the resulting clusters. The color in the figure below represents the number of peaks from each experiment that fall within each significant clusters. The order of clusters in the positive tail map is also a representation of the relationship between clusters. For example, cluster 1, 2, 23, 12, 6, 22 are not geometrically closer, but they are reported by the same studies, so they might come from the same brain network. It is also possible to share and edit a meta-analysis. After running the selected meta-analysis in Google Colab, you might notice a link for viewing the completed meta-analysis, which will then direct you to the NeuroVolt collection link. All the statistical map generated by meta-analysis will be put on NeuroVolt. It is reproducible because this NeuroVolt link can be shared to anyone. It is easy to clone an existing dataset and add your own data. For example, after running the meta-analysis on nicotine administration dataset, all the statistical map will be shared on NeuroVolt, including the FDR-corrected P-map, FDR-corrected Z-map, uncorrected P-map, uncorrected Z-map, as well as the activation intensity map. Now it's your turn to run your own meta-analysis and interpret the result using NeuroSynth-Compose with the nicotine administration dataset. You can also follow the instructions on the meta-analysis book with the link below. Please let me know if you have any questions. Thank you.